Welcome viewers, in this video we'll see the introduction about the transient available in the circuit theory. Subscribe the channel for more videos and notifications. Soft copy of this material available in the drive. The link is given in the description box. Now we'll go to the topic transient. We'll see the introduction about the transient. A circuit having constant sources is said to be in steady state if the current and voltage does not change with the time. So the steady state means having the constant sources, voltage or current source, that will not change with respect to the time. Then it is called a steady state. Thus, circuit with currents and voltage having constant amplitude and constant frequency, sinusoidal function, and also considered to be in a steady state. That the circuit with the current and voltage, constant amplitude and constant frequency in sinusoidal function, that also considered as a steady state. So that means the amplitude or frequency of the sinusoidal never changes in a steady state circuit. So the steady state circuit means amplitude or frequency remains same, that will not change with respect to the time. Then it is called a steady state. Then what is about the transient state? Steady state we know very well, that is the amplitude and frequency is not changing with respect to the time. Then what about the transient state? In a network containing energy storage elements, with change in excitation, the current or voltage change from one state to other state. So the circuit contains the energy storage elements, that is inductor and capacitor. So when the excitation is there, the voltage and current is changing from one state to other state. The behavior of the voltage or current when it is changed from one state to another state is called a transient state. So that is due to the energy storage element. Current or voltage change from one state to another state, that is called a transient state. Right. Now we'll see the transient time. What is the transient time? The time taken for the circuit to change from one state to another state is called a transient time. The time taken to change from one state to another state is called a transient time. Transient state means one state to another state, for which how many time taken is called a transient time. Right. I will see the natural response. What is meant by natural response? The application of KVL and KCL, Kirchhoff's voltage law and Kirchhoff's current law, to circuit containing energy storage element result in differential rather than algebraic equation. We got the differential equation, di by dt, dv by dt, not a algebraic equation, due to the energy storage element. When we consider a circuit containing energy storage which are independent of the sources, independent of the sources, response depends upon the nature of the circuit, then it is called natural response. Right? So when the natural response means the circuit containing storage element independent of the source, but it depends upon the nature of the circuit, that is called natural response. Then transient response. Storage element delivers their energy to the resistance. Hence, the response changes with time and gets saturated after some time, and it is referred as a transient response. Right? The storage element delivers the energy to the resistance. So the response changes with the time, gets saturated after some time. So this is called a transient response from one state to another state. Then forced response. Now we'll see what is the forced response. When we consider sources acting on a circuit, the response depends upon nature of the source or sources. In earlier case, natural response means not depends upon the source, that is depends upon the nature of the circuit. If we consider source or nature of the source, then this response is called forced response. So here the response depends upon the sources. Natural response means sources will not affect the circuit, but the circuit, nature of the circuit itself is called a natural response. That is depends upon the nature of the circuit. Right. So in this we'll see the final conclusion. In other words, the complete response of the circuit consists of two parts: forced response, transient response. Forced response means that is due to sources. Transient response means due to storage element changes from one state to another state. Right. When we consider differential equation, the complete solution consists of two parts: the complementary function, particular solution. So that is depends upon the differential equation. By solving this, we can go for further. So in this video, we discuss what is meant by transient. That is, first we studied what is steady state. Without changing the amplitude, it's called a steady state. When the amplitude changes from one state to another state, that is called a transient state. Time taken is called transient time. Then natural response and forced response, that is purely depends upon the source. If the source is not affecting the circuit, means natural response. If the sources affecting the nature of the circuit, means it is a forced response. Right. Then transient response means the storage elements that deliver the energy to the resistor. That is called a transient response. In this case, we got in KVL, KCL, we got the differential equation also. In that time, we can go for complementary function and particular solution. Subscribe the channel for more videos and notifications. Soft copy of this material available in the drive. The link is given in the description box. Thank you for listening. Welcome viewers. In this video, we will see the initial condition in the network element for inductor. Subscribe the channel for more videos and notifications. Soft copy of this material available in the drive. The link is given in the description box. Now we'll go to the topic, the inductor, network element inductor. What is the initial condition? While going with the transient, what are the initial conditions available in inductor? Let us consider the inductor L. The current IL is flowing through the inductor. The voltage across the inductor is VL. The relation between current flowing through the inductor and voltage across is given by VL equal to L dIL by dt. Voltage across the inductor equal to inductor and dIL by dt. Right. If DC current flows through, dIL by dt become 0. In the DC current means the differential of the current dIL by dt become 0, as DC current is constant with respect to the time. Right. So VL equal to L dIL by dt. dIL by dt becomes 0 in case of DC because the constant current is constant. Hence voltage across inductor VL become 0. Thus, as far as DC quantities are considered, in steady state, inductor acts as a short circuit. So we got the first case. In case of DC, the voltage across the inductor is 0 because of constant. Current is constant. So, applying the DC quantity, the inductor is act as a short circuit. Right. Now we'll go to the next. We can express the inductor current in terms of voltage developed across it. So this is the expression for current. IL equal to 1 divided by L integral VL dt. Right. So it is rearranged. The equation is rearranged. So current is given in terms of voltage. Right. IL equal to 1 by L integral VL divided VL dt. Now we'll go for the analysis of this inductor current. In above equation, the limits of integration are decided by considering past history, previous history, that is minus infinite to t0 minus, right? Infinite, minus infinite to t0 minus, assuming that switching takes place at t equal to 0. So we can split the limit into two intervals, minus infinite to 0 minus to t, right? It is divided into t because in between we are having 0 is available. So minus infinite to 0 minus to t, right? Now we'll go for further. We have already studied that 0 minus is the instant just before switching action takes place. 0 plus means after switching. 0 minus means before switching. So while 0 plus is the instant just after the switching action takes place, right? So the limit is from minus infinite to t minus t0 minus, because of t equals 0 switching takes place. So it is splitted into minus infinite to 0 minus to t. What is 0 minus and 0 plus? 0 minus means before switching action. 0 plus means immediately after switching action. Now we'll see the equation. What happened to the equation? Current equation. Hence we can write IL equal to 1 by L integral minus infinite to t VL dt. Now that is split into 2. 1 by L integral minus infinite to 0 minus VL dt plus 1 by L 0 minus to t VL dt, right? So it is split into minus infinite to 0 minus to t. Now we'll go for this. First term on RHS of equation represent value of inductor current in history period, which is nothing but initial condition of IL. Minus infinite to 0 minus means before switching, initial condition. So let it be denoted as IL 0 minus, right? We already discussed 0 minus mean before switching. So this entire term refer the initial condition of the inductor, that can be represented as IL 0 minus. So due to that, the equation, we can write the equation as IL inductor current equal to IL 0 minus. The term is replaced plus 1 by L integral 0 minus to t VL dt, right? At t equal to 0 plus, we can write what is 0 plus? After switching. 0 minus mean before switching, it is after switching. That is equal to IL 0 minus plus 1 by L 0 minus to 0 plus VL dt, right? So this t, now it is replaced by 0 plus because t equal to 0 plus immediately. So this equation is nothing but after. 0 plus means after switching, 0 minus before switching. So this initial condition, initial current while switching, what happened before and after the switching, right? So initially we have assumed that switches act in a 0 time. Thus integration from 0 minus to 0 plus is 0. What we assume that the switch act in a 0 time. So there is no before switching, after switching. That is, we assumed as 0. Immediately we switched on. So that IL 0 plus equal to IL 0 minus. This term is 0 because we assume that 0 time. Before and after switching 0 time. Thus this term becomes 0. So IL 0 plus equal to IL 0 minus. This is nothing but initial current. This is final current. Both are equal. Initial current and final current is equal. Thus current through inductor cannot change instantaneously. That means the current through inductor before and after the switching action is same, right? So we conclude that current flowing through the inductor is not changes instantaneously. That is the main property of the inductor. It will allow the current to increase or decrease in a gradual manner, not a suddenly, instantaneously. So that before and after switching action, the current is through the inductor is same, right? Now we'll go for the next condition. At the time of switching, the voltage across inductor is ideally infinite as interval dt is 0. Right? The voltage across the inductor is ideally infinite as the interval dt is 0. Thus, at the time of switching, inductor acts as a open circuit, while in steady state at t equal to infinite act as a short circuit as given. That we already discussed that is short circuit, right? So at the time of switching it acts as a open circuit, after switching it acts as a short circuit, right? Now we'll see the further. If inductor carries an initial current I0 before switching action, then at instant t equal to 0 plus, it acts as a constant current source of value I0. So what we discussed earlier is initial current is 0. We assume that initial current is 0. Initially now current. But here, if the initially current is available means it acts as a current source, constant current source. While in steady state at t equal to infinite, it acts as a short circuit across a current source as given. Earlier only short circuit. Now before switching current is available. So it acts as a short circuit across a current source. Both are connected in parallel, short circuit and current source. So this is the initial condition details about the inductor. First one is if the DC quantity means the inductor acts as a short circuit. Right. Then current. We have two conditions, before switching, after switching. We assume that there is a before and after switching time is 0. So due to that, the current before switching current and after switching current is equal. We caught the term both are equal. So that it acts as a inductor will not allow sudden change in current. It will increase gradually or decrease gradually. Right. So that before and after switching the current is same. Then we discuss about it is act as a short circuit. Under steady state condition it acts as a short circuit. Suppose the initial current is available means short circuit with current source. So that is the detail about the initial condition of inductor. Subscribe the channel for more videos and notifications. Soft copy of this material available in the drive. The link is given in the description box. Thank you for listening. Welcome viewers. In this video we will see the initial condition in network elements, this capacitor. Subscribe the channel for more videos and notifications. Soft copy of this material available in the drive. The link is given in the description box. Now we'll go to the topic capacitor. What is the initial condition while applying the voltage, while switching, before the switching, after the switching? What is the initial condition in the capacitor? Let us consider the capacitor C. In this, the current flowing through the capacitor is IC, voltage across the capacitor is VC. The relation between current and voltage across the capacitor is IC equal to C into dVC divided by dt. So this is the current flowing through the capacitor. IC equal to C, capacitor into voltage dVC divided by dt. If the DC voltage is applied to the capacitor, dVC by dt become 0 as the DC voltage is constant. Suppose if you apply the DC voltage, then this term dVC by dt become 0 because the voltage is constant in case of DC. Right. So based on that, with respect to the time, the DC voltage is constant with respect to the time. Hence the current through the capacitor is 0. IC becomes 0. Thus, as far as DC quantities are considered, the capacitor acts as a open circuit, right? So, IC equal to C into dVC by dt. This term dVC by dt is 0 as DC voltage is constant with respect to the time. So that the current flowing through the capacitor is 0. So, for the DC quantity, the consider capacitor is act as a open circuit. So if you apply the DC quantity, the capacitor act as a open circuit. Now we can express the voltage across the capacitor in terms of the current. Earlier we discussed the current through the capacitor IC. By rearranging that equation, VC equal to 1 divided by C integral IC dt. So this is the voltage across the capacitor. The terms are rearranged with the limit VC equal to 1 divided by C integral minus infinite to T IC dt. Right. So the charging from minus infinite to time T. Splitting the limit of integration. So we can split the limit. VC equal to 1 divided by C integral minus infinite to 0 minus IC dt plus 1 by C 0 minus to T IC dt. Right. So minus infinite to T is splitted into minus infinite to 0 minus to T. Now we'll see what is the minus infinite to 0 minus. The first term denoted as VC 0 minus. Right. So this term can be expressed as VC 0 minus, that is before switching. right? At T0 plus, the equation is given by Vc 0 plus. So this is the Vc 0 plus equal to Vc 0 minus. Minus infinite to 0 minus is expressed as voltage across the capacitor before switching, plus 1 by C integral 0 minus to 0 plus IC dt, right? So this equation is now rearranged as Vc 0 plus equal to before after switching equal to voltage across before switching plus voltage 1 divided by C 0 minus to 0 plus IC dt, right? Now we'll see what happened further. So as switch act in 0 time, the integration from 0 minus to 0 plus is 0. So this is 0 minus is before switching, 0 plus is after switching. So we consider that this is 0 time. There is no time delay between before switching and after switching, right? So that 0 minus to 0 plus is 0. There is no 0 time. There is a switch is act as at 0 time. There is no delay between before switching and after switching. So that above equation Vc 0 plus equal to Vc 0 minus. The second term is 0, right? That is the integral between 0 minus to 0 plus is 0. Thus, the voltage across capacitor cannot change instantaneously. Before switching, after switching, the voltages are equal. That is the conclusion we got from the above equation, right? So the voltage cannot changes instantaneously, right? Now we'll go for the further analysis. In the network, if uncharged capacitor is present, then the current start flowing through it instantaneously when excitation is given to the network. Suppose if the uncharged capacitor is available, mean it will start charging. So the current flowing through it instantaneously when the excitation is given. So at the instant T0 plus, that is after switching, capacitor acts as short circuit. Once get charged at T equal to infinite, in steady state it acts as a open circuit, right? So uncharged capacitor is available, then it will current start flowing through it instantaneously when the excitation is given. So at T0 plus it acts as a short circuit. After fully charged at T equal to infinite, it acts as a open circuit, right? So that is the conclusion we got. If initially capacitor is charged to the voltage V0, earlier uncharged, this one initially charged before switching, then at instant T0 plus, 0 plus means after switching, it acts as a constant voltage source because already charges is available, it will start discharging. So it acts as a constant voltage source of value V0, right? So the already is charged, the capacitor is charged at V0. While in steady state at T equal to infinite, it acts as a open circuit in series with the voltage source, right? So earlier this uncharged means while charging it acts as a short circuit, after fully charged it acts as a open circuit. If it is already charge is available, means it acts as a constant voltage source because already charges are available at T equal to 0 plus. At T equal to infinite, after fully at a infinite value, it acts as a open circuit in series with the voltage source, right? Because of fully charged voltage source is there, at infinite it acts as a open circuit in series with the voltage source. So in this video we discuss about what is the initial condition of a capacitor. When it is connected across the DC source, this acts as a open circuit because dVc by dt is 0. So totally the current flowing is totally 0. Then for other cases, when it is fully already not charged, uncharged means it acts as a short circuit initially, after fully charged it acts as a open circuit. If already charged is available, initially charge is available means it acts as a voltage source, constant voltage source, thereafter it acts as a open circuit in series with the voltage source. Subscribe the channel for more videos and notification. Soft copy of this material available in the drive. The link is given in the description box. Thank you for listening. Welcome viewers. In this video, we'll see the behavior of the network elements. Effect of switching on circuit element, that is during transient. During transient, what is the behavior of the network elements? Resistor, capacitor and inductor. Subscribe the channel for more videos and notification. Soft copy of this material available in the drive. The link is given in the description box. Now we'll go to the topic. First element we'll consider the resistance. There are two cases we'll see. Behavior immediately after the excitation is given, T0 plus instant, after closing the switch. Behavior as T tends to infinite, that is steady state. After steady state. So after immediately switching close, T equal to 0 plus, and also T tends to infinite at steady state. In case of resistor, there is no change. During the, before switching the, or after switching, or after steady state, it behaves same as. There is no change in current or voltage in case of the resistance. Right. Now we'll go to the inductance. What will happen to the inductor? So inductor is available. So it acts as a open circuit. Immediately after closing the switch, it acts as a open circuit because the inductor will not allow sudden change in current. While applying the DC voltage, it acts as a open circuit. After steady state, it acts as a short circuit. Right? Immediately after closing, it acts as a open circuit, thereby short circuit. Suppose already the current is flowing through a inductor, then it acts as a current source. It acts as a current source. After steady state, it acts as current source in parallel, short circuit in parallel with the current source. So what available here? Short circuit. But due to the current, here the current source also available. So current source and short circuit in parallel. Right? So immediately after closing, it acts as a open circuit. Right? Thereafter under steady state, it acts as a short circuit. If already current is flowing, it acts as a current source. Because of already current available, it acts as a current source. In the steady state condition, current source and short circuit are available in the parallel. Right. Now we'll go to the capacitor. Now we'll see the details about the capacitor. This capacitor, it acts as a short circuit. At the instant immediately closing the switch, it acts as a short circuit. If it is fully charged, then it is act as open circuit. During charging, it acts as a short circuit. After fully charged, it acts as a open circuit. Suppose already voltage is available. Suppose already the voltage is available in the capacitor, it acts as a voltage source. Earlier, current is available in inductor, means it acts as a current source. Here voltage is available, so it acts as a voltage source. Right. So after fully charged, discharged, what happened? It acts as a voltage source in series with the open circuit. Right. So during charging, it acts as short circuit. After fully charged, open circuit. Already voltage available means act as voltage source. Under steady state condition, voltage source and open circuit, because at steady state there is no charging or discharging, so that it acts as a open circuit. So in this video we discuss about the behavior of the network elements, resistor, inductor and capacitor. The resistor acts as a same during switching, after switching or steady state. Inductor acts as a open circuit, thereby short circuit under the steady state condition. If already current is flowing means it acts as a current source in steady state, current source in series with, in parallel with the short circuit. Right. The capacitor means it acts as a short circuit. It will start charging. After fully charged under steady state, it acts as a open circuit. If already voltage is available means it acts as voltage source. Under steady state, voltage source in series with the open circuit. Subscribe the channel for more videos and notification. Soft copy of this material available in the drive. The link is given in the description box. Thank you for listening. Welcome viewers. In this video, we will see the DC transient response of RL circuit. Case 1, rise of current. Subscribe the channel for more videos and notification. Soft copy of this material available in the drive. Link is given in the description box. Now we'll go to the topic. DC transient response of RL. Resistance and inductance are connected in series circuit. The case 1, rise of current. Let RL series combination be impressed upon the DC voltage E by closing the switch K. Resistor and inductor is connected in series, that is energized by the voltage E, DC voltage source E, that is by closing the switch K. Assume that current through the inductor before closing the switch is 0. So before closing the switch there is no current, there is no flow of current. Let K be the closed at the instant t equal to 0. Switch is closed at t equal to 0. Now consider this diagram, circuit diagram. So this is the RL series circuit. R and L is connected in series, energized by the DC source and controlled by the switch K. The voltage across resistor is ER, voltage across inductor is EL. Right. So after closing the switch, is closed at t equal to 0, the circuit behave like this. The inductor acts as a open circuit. This is a voltage source, resistor, and it will act as a open circuit. Right. Now we'll go for, in order to find the time response, we need to apply the KVL, Kirchhoff's voltage law, to this circuit, and we need to find the equation. Then we can apply Laplace transform and inverse Laplace transform to get the time response. Okay, while applying the Kirchhoff's voltage law, what will happen? The applied voltage E equal to voltage drop across resistor and inductor. So E equal to R into I plus L di by dt. R into I is the voltage drop across resistor, L di by dt is the voltage drop across inductor. Right. So according to KVL, the voltage, this is voltage rise, this is voltage drop, both are equal. So voltage applied E equal to drop across R and L. Right. Now we'll see the diagram how to apply the Kirchhoff's voltage law. So the equivalent circuit at T0 plus is shown in figure B. That is, inductor is open circuited. T0 plus means after closing the switch. The inductor is shown as a open circuit. Hence, I0 minus equal to I0 plus equal to 0, because before closing we assume that there is no current flow. After closing it is act as a open circuit. So current before closing the switch, after closing the switch is 0. Right. Then we go for the applying the Kirchhoff's voltage law to the circuit after t seconds of closing K. After closing the switch, we can apply the Kirchhoff's voltage law. We already discussed the applied voltage E equal to resistive drop plus inductive drop, Ri plus L di by dt. You take, this is the equation number 1. Resistive drop, inductive drop, that is equal to E, applied voltage E. Now we can take the Laplace transform on both the sides by converting t domain into s domain. Again, by taking inverse Laplace, we will get the t domain, time response. First we will take the Laplace transform. So while taking Laplace transform, it is nothing but R into I of t become I of s plus L. This di by dt is nothing but s into I of s minus I0 plus. This is the initial condition. That is equal to Laplace transform of E is E by S. Right. So R into I of s plus L of s I of s minus I of 0 plus, that is equal to E by S. Right. So di by dt, Laplace transform of di by dt is s into I of s minus initial condition. Then R into I of s plus L, s into I of s, this initial current. We already discussed that the current before closing, after closing the switch is 0. This value is 0. That is equal to E of s. Now we will take the I of s outside. So that R plus s into L, that is equal to E by s. I of s equal to R plus SL equal to E of s. Now we can go for the further simplification. So that I of s equal to E divided by s into R plus L of s. This term is brought in the denominator. Now we'll take the L outside. So that already s is there, L into s plus R by L. While taking the L outside, this becomes s. Here L is not available, so that R by L. So now in order to bring s plus form, s plus R by L, we are taking L outside. Now take this equation number 2. So I of s equal to E divided by L into s of S plus R by L. Right. Now we'll take the partial fraction. In order to take the inverse Laplace, we need to split the term. Then only we can take the inverse Laplace. Let us consider E divided by Ls into S of R divided by L can be written as A by S plus B by S plus R plus R by L. This is called a partial fraction. So the terms, two S terms are splitted. Then only we can able to find the inverse Laplace transform. Now we can go for the simplification. So this term E divided by Ls of S plus R by L equal to, take the LCM, S into S plus R by L. Here S is available, so it is multiplied with this term. Here S plus RL is available, so multiplied with S, right? So A into S plus RL plus B into S. These terms are multiplied. This term is multiplied with A, this term is multiplied with B in order to simplify. Now this S got cancelled. Similarly, S plus RL also available on both the side, right? So after cancelling the term, we will see that what happened. E by L equal to A into S of R plus L plus BS, right? This denominator terms are cancelled. This is equation number 4. E by L equal to A of S plus RL plus BS. Now what the next step is, we need to find the value of A and B. Then only we can go for inverse Laplace transform. Then how to find that? By putting S equal to 0, we can, this term got cancelled, so that we can find the term A. By putting S equal to minus R by L, this term become 0, so that we can find the term B. So that is our idea, right? Put S equal to 0, so that we can find value A. Put S equal to minus R by L, so that we can find the value BS, right? First we will put S equal to 0 in equation number 4. This is the equation number 4. So while putting S equal to 0, what happened? E by L equal to A into this S is 0 plus R by L plus B into S is 0. So this term becomes 0. So E by L equal to A into R by L. L got cancelled. So E equal to AR. So A equal to E by R, that is A equal to E by R, right? So that now we calculate the term A, constant. A is E divided by R, right? Now we need to find the term B. In order to find the B, we are substituting S equal to minus R by L. This S is substituted as minus R by L in equation number 4. Now substitute S equal to minus R by L in equation 4, so that E by L equal to A plus, this is S. S is replaced by minus R by L plus R by L plus B into minus R by L. So this is minus R by L plus R by L, so got cancelled. It become 0. So E by L equal to A of 0, here negative available, minus B into R by L. So that E by L equal to minus B into R by L. L got cancelled. E equal to minus BR, so that minus B equal to E by R. That is B equal to minus E by R, right? Now we calculated the constant B also. A already calculated as E by R, B equal to minus E by R. Now we can substitute this value and we can go for the inverse Laplace transform. Substitute the value of A and B in equation number 3. So this is equation number 3. E divided by Ls, S plus R by L equal to A by S plus B by S plus R by L, right? So A is substituted as E by R, B is substituted as minus E by R. So that it is nothing but E divided by S into R minus E divided by R of S plus R by L, right? So now we can take this E by S, E by R is commonly available. So E by R is taken outside. So that E by R of 1 by S minus 1 divided by S plus R by L. So take this equation number 5, right? Now we'll go for the further. So this term now is replaced as this E by R of 1 by S minus 1 by S plus R by L, right? Substituting the above value in equation number 2, second equation, so that I of S equal to E divided by Ls S plus R by L. This is equation number 2. So now this value is replaced by E by R of 1 by S minus 1 by S plus R by L, right? So this time we cannot take the inverse Laplace, so that we use the partial fraction. We identify the value of, we calculated the value of A and B, that is substituted. After substitution we got this. Now we can easily take the Laplace transform on both the side, inverse Laplace on both the side. So while taking inverse Laplace, this I of S become I of t, then E by R. 1 by S, the inverse Laplace of 1 by S is 1. Similarly 1 divided by S plus R by L is nothing but this, using this formula. 1 divided by S plus A equal to E power minus AT. This is the Laplace transform. So 1 divided by S plus R by L. Here A is nothing but R by L. So that E equal to minus R by L t. Right? So inverse Laplace of this 1 divided by S plus RL is E of minus RL by t based on this formula. E of minus AT. Now this is equation number T. So this is the time response of the RL circuit. Case 1, rise of current. We got that I of t equal to E divided by R of 1 minus E power minus RL by t, R by L into t. Right. Now we'll go for the further analysis. I equal to E by R is called a steady current. E by R. This E by R can be written as I. Then L by R is the time constant of RL circuit. L by R equal to tau. That is time constant. So based on that we can write I equal to capital I, steady current of 1 minus t into tau. This t is written as it is R by L minus R by L, but L by R is tau, but here R by L, so 1 by tau. So minus t by tau. So equation number 8. So I equal to I, steady current of 1 minus E power minus t by tau. By analyzing the nature of this equation, the above equation shows that as t increases, I increases exponentially. So when the current increases, when the time increases, current also increases exponentially. Actually this term is decreasing, but 1 minus is there, so that it is increasing, right? So t increases, I also increases. Now we'll go for further analysis. The transient voltages ER and EL across R and L respectively during the rise of current in the inductor can be expressed as. Now we calculated the time response of the current. Now we'll calculate ER and EL, voltage across resistor and inductor. So ER is nothing but R into I, resistor value into I. So R into I is already calculated. I of 1 minus E power minus t by tau. Right. Similarly, ER equal to E into, so this R, I into R is written as E, right? Applied voltage 1 minus E power minus t by tau. So this equation number 9. So this equation number 9, we can say that voltage across R increases exponentially from 0 to E during the rise of current. Already told this is the decreasing, but 1 minus t means increasing, right? So when the rise of current, the voltage is increases from 0 to E. It's a rise, increasing, voltage increasing from 0 to E during the rise of current. Similarly, what is the voltage about? Voltage across the inductor, EL. So by using the Kirchhoff's voltage law, ER plus EL equal to E. We already discussed. So EL equal to E minus ER. The ER is already calculated. E into 1 minus E power minus t by tau, voltage across the resistor. Thus E is commonly available, so we can cancel. This is multiplied inside. E minus multiplied. Minus E plus E into minus t by tau. This E got cancelled. So only we have E. EL equal to E power minus t by tau. From equation 10, we can say that the voltage across L decreases with the time t exponentially. Already told this is the decreasing part. In previously what we have 1 minus E power. So that decreasing, but because of 1 minus it is increasing. But here 1 minus not available. Only this term is available, so that decreasing. Voltage across the inductor decreases when the time increases. Right. So this variation of I of t is shown in the diagram. Similarly, ER and EL also shown in the next diagram. Diagram A shows the variation of the current I of t. Diagram B shows the variation of ER and EL. Right? So we already discussed that it is increasing. The current is increases with respect to time. When the time increases, current is increasing. So this is about 0.632 times of I at the time t. Thereafter it is increases. This is the total current. I equal to E by R, steady current. Right? So after analyzing, we are able to say that when the time increases, the current through the circuit increases exponentially. Right. Similarly, voltage across the resistor also increasing from 0 to E. But the voltage across inductor is decreasing. We already discussed that it is keep on decreasing exponentially. Right. So current increases exponentially with respect to time. Voltage across the resistor also increasing exponentially with respect to time. The voltage across the inductor decreasing exponentially with the time. Now we'll go for the time constant of RL circuit. Now definition of time constant T for RL circuit. Substitute tau equal to T in equation 8. So I equal to I of 1 minus e power minus t by tau. Now we are replacing tau equal to T. So minus t by t is nothing but minus 1. I equal to I of 1 minus e power minus 1. So that is I equal to I 1 minus, this is nothing but 1 by E. Either e power minus 1 or 1 by E. That value is 0.3679. So 1 minus this value is 0.6321. So I equal to 63.22 percentage of I. So this only we saw in the graph. The current increases gradually. After 63.2, it is up to this value, it is increasing exponentially, rapidly. Thereafter slowly increasing. So this is the 63.22 percentage of current. Corresponding time also indicated in the graph. Right. So from this we can able to conclude that thus the time constant of RL series circuit is defined as the period during which the current rises to 63.2 percentage of its final value or steady value. Right. So this is the time constant. While the time taken to reach 63.2 percentage of current is nothing but a time constant of the RL series circuit. So in this video we discuss about the DC transient response of RL circuit. R and L is connected in series. For the case 1, rise of current, we discuss how the current behaves as well as voltage across the inductor and voltage across the resistor. Finally, we calculate the time constant. 63.2 percentage of current reaches. That is called a time constant of RL circuit. Subscribe the channel for more videos and notification. Soft copy of this material available in the drive. The link is given in the description box. Thank you for listening. Welcome viewers. In this video, we will see the DC transient response of RL circuit, case 2, decaying transient. Subscribe the channel for more videos and notification. Soft copy of this material available in the drive. The link is given in the description box. Now we'll go to the topic. DC transient response, RL circuit, resistance and inductance. Case 2, decaying transient. Case 1, rise of current available in the separate video. Now see the circuit diagram. The R and L is connected in series. It is energized by the DC source E. The switch is available. There are two positions are available. When the switch is connected to the position 1, the DC voltage is applied to the R and L. When the position is connected to 2, the source is disconnected. The source is disconnected, only R and L will be connected. Right? Now we'll see the statement. Assume that the switch is kept connected in to position 1 for sufficient longer period. For sufficient longer period, the switch is kept in the position 1. That is, it is connected with the DC source. Then the current reaches the steady state value, which is given by I equal to E by R. Due to longer period, the current is slowly increases and reaches the steady state value. That is nothing but E by R. So after this period, let the switch is moved from position 1 to position 2. First kept in the position 1 for longer time, the current keep on increases and reaches the steady state value I equal to E by R. After that period, the switch is moved to the second position. position 2. Right. Now we'll see what happened in the position 2. Let the instant be taken as t dash equal to 0. After t dash seconds of closing the switch to the position, apply KVL. Right. In the position 2, the source is disconnected, only R and L is connected. So by applying KVL is nothing but resistive drop plus inductive drop equal to 0. The applied voltage is not available. In position 1, voltage source is connected. In position 2, not connected, disconnected. So the resistive drop is Ri plus inductive drop is L di by dt, that is equal to 0. We take this equation number 1. Right. In order to get the transient response, we need to take the Laplace transform and inverse Laplace transform, so that we'll get the time response. Taking Laplace transformation on both the sides, we get. So Ri is nothing but R into I of s. This t domain is converted into s domain while taking Laplace transform. L di by dt, L into the Laplace transform of di by dt is s into I of s minus I of 0 plus equal to 0. This is nothing but initial condition. This is the initial value. So I 0 plus, that is after closing the switch. Right. That is E by R. The current is after closing the switch, what is available is E by R, because before going to the position 2, the switch is kept in position 1. So the current is slowly increases and reaches the steady state value, that is given by E by R. So after closing the switch, the initial condition of the inductor is current. This much of current is available. So this I of 0 plus is E by R. Now we substitute the value S in R into I of s plus multiply inside Ls I of s minus I naught, L into I naught of I of 0 plus, I of 0 plus is E by R, that is equal to 0. Right. This value is replaced by E by R. Now take this I of s common, so that R plus Ls, right, minus, so bring this minus L E by R that side, so that it becomes plus L E by R. This E by R is nothing but I, right. So that I of s equal to R plus Ls, that is equal to L into R, I. So bring this term in the denominator, so that I of s equal to L into I divided by R plus Ls. Now we got the expression for current, that is L I divided by R plus Ls. This is the initial current. Now we'll go for the further simplification. So this L got cancelled. So we got I divided by S plus RL, right? So it is nothing but a form S plus A. A is nothing but R by L. Now by taking the inverse Laplace transform on both the side, we'll get the current in the time response, right? So by taking the inverse on both the side, this I of s is become I t dash. We already know that after the instant moving from position 1 to position 2, it is taken as t dash. That is equal to Laplace inverse of I of s. Laplace inverse of I divided by s plus R by L is nothing but e power minus R by L t dash. So it is based on this formula. 1 divided by s plus A equal to e power minus AT. Here A is nothing but R by L. So that e power minus R by L t. Right. So that it is nothing but I of t equal to minus t dash divided by tau. What is the tau value? Tau is nothing but a time constant of RL circuit. That is L by R equal to t. Tau, that is time constant of RL circuit, right? L by R. But here it is available R by L. So that it is 1 by tau, right? L by R is tau, R by L is 1 by tau. So I of t dash equal to I into e power minus t dash divided by tau. That is the time constant, right? Now we need to analyze this equation, right? I equal to what happened, whether increasing or decreasing, we need to analyze. Thus I decays. So this is nothing but the decaying. E power minus t means decreasing value, right? So we can easily identify that. 1 minus e power means this is decreasing, but while going 1 minus e power increasing. But here by seeing the equation, we clearly say that it is decaying. Thus I decays exponentially from I to 0. So I is reaching from, keep on decreasing from the maximum value I to 0 at t dash, increases from 0 to infinite. When the time increases from 0 to infinite, current decreases from I to 0. The variation of I of t dash with respect to t dash is shown below. Right. See, this is the time. When the time increases, the current is keep on decreases, exponentially decreases. This I is nothing but E by R. Right. This is I. Right. From the equation we identify that the current is decreases from I to 0 when the time increases from 0 to t dash. Now we can see the variation of the voltage across resistor and inductor. Decaying current in RL circuit. ER equal to R into I. Voltage across the resistor is R into I. R into I is nothing but I e power minus t dash divided by tau. So see that this is also decreasing. Right? I into R into I is E. So ER equal to E power minus t dash by tau. So we can easily see that this voltage across the resistor also decreasing. So by using the KVL, EL plus ER equal to 0, so that EL equal to minus ER. So that is equal to minus E power minus t dash by tau. The ER already available, so minus. So this is also decreasing, but in the negative region. Decreasing in the negative region. Right? So we already identified that current is decreasing from I to 0 when the time increases 0 to t. The voltage across resistor and inductor also decreasing. Right? But inductor decreasing in a negative region. Now we'll see the graph for this EL and ER. So this is the time t dash. Here E is available. We already identified that voltage across the resistor decreases from maximum value, it keep on decreases. This EL, voltage across inductor also decreases, but in negative region, minus E, it is also decreasing, increasing, but it is in the negative region, means it is decreasing. Right? Both are in a decreasing manner, but ER in positive, ER in negative region. So in this video we discuss about the transient response, DC transient response of RL circuit. In the case to decaying, we identify the current I of t, say that it is decreasing from I to 0 when the time increases from 0 to t. And also current voltage across resistor and inductor also decreasing, inductor in the negative region. Subscribe the channel for more videos and notification. Soft copy of this material available in the drive. The link is given in the description box. Thank you for listening. Welcome viewers. In this video we will see the DC transient response of RC circuit, case 1 charging. Subscribe the channel for more videos and notification. Soft copy of this material available in the drive. The link is given in the description box. Now we'll go to the topic. DC transient response of RC circuit, resistance and capacitance, case 1 charging. Let us consider this resistor and capacitor connected in series. It is energized by the DC source E and controlled by the switch. By closing the switch, the voltage is applied. The Q0 is the initial charge available on the capacitor. I will see the description. Consider the RC series combination. A DC voltage is applied to the combination through the switch. Let Q0 is the initial charge on the capacitor. Initially the charge is available. So the initial voltage on the capacitor is V0 equal to Q0 divided by C. Right? Q equal to Vc. This is a formula, so that V equal to Q0 divided by C. V0 equal to Q0 divided by C, initial voltage. Right? Now we need to go for the time response. For that we need to apply the Kirchhoff's voltage law to this circuit. While applying Kirchhoff's voltage law, what is the equation? The applied voltage E equal to resistive drop plus capacitive drop. Voltage across the resistor plus voltage across the capacitor. That is E equal to I into R. The voltage drop is I into R. The voltage drop across capacitor is 1 by C integral I dt. So that is the KVL. Now we'll go for applying the Kirchhoff's voltage law for the given circuit, RC series circuit. At t seconds of closing the switch, apply KVL to the circuit. So that IR plus IC integral minus infinite to t I dt equal to E. So the applied voltage equal to resistive drop plus inductive drop. Right, I into R plus 1 by C. This minus infinite to t is split into two terms. Minus infinite to 0, 0 to t, I dt. Right. So this minus infinite to 0 is nothing but the initial voltage. That is V0. We already discussed. V0 equal to Q0 divided by C. Right. So this is the 0 to t is the after closing the switch. This is before closing the switch, initial state. So that voltage is V0. So that we can write this is equation number 2. The equation number 2 can be written as IR plus V0 plus 1 by C. This V0, this is the initial voltage. This term is replaced by V0. 1 by C integral 0 to t I dt, that is equal to E. 0 to t means after closing the switch. In the present case, let us assume that the initial charge on the capacitor is 0. Hence V0 equal to 0. Earlier we assumed that initial charge is Q0. Now at present we are assuming that there is no initial charge. So V0 is 0. So we can modify this equation. This V0 become 0. So substitute V0 equal to 0 in the equation number 3. So it become IR plus IC. This is IR, means I into R, resistance into current. 1 by C, 0 to dt, I dt equal to E. You can take this is equation number 4. Now we can take the Laplace transform so that the t domain can be converted into S domain. Again by taking inverse Laplace we will get the time response. Right. So I into R. R is constant. So integral of I, the Laplace transform of I is I of S. This is t domain. Now converted into S domain. 1 by C. So integral 0 to t I dt. That is by taking the Laplace transform of integral is nothing but I of S divided by S. Right? Differentiation means S into I of S. Integral means I of S divided by S. Differentiation multiplied, integration divided. The Laplace transform of E is E by S. Right? Now we taken the Laplace transform on both the sides. This I of S is available commonly. Take outside. So its R is available here. Here 1 divided by C into S is available. That is equal to E by S. Right. Bring this term in the denominator on this left hand side so that I of S equal to E divided by S already available. Then this term R plus 1 divided by CS. Right. Now we can go for the further simplification. Multiply S inside. So S into R plus 1 divided by CS. So S got cancelled, 1 by C. Now take the R outside in order to bring the S plus A term. Then only we can take the inverse Laplace. So this R is taken outside. So S plus, here R term is not available. So it is divided, 1 divided by RC. Right. So finally we got this value I of S equal to E divided by R into S plus 1 by RC. Now we can take the inverse Laplace. Now taking inverse Laplace on both the sides. So I of S become I of t. E by R is constant. 1 divided by S plus R 1 plus S plus 1 by RC is E power minus t by RC. So that is based on this value. 1 divided by S plus A equal to E of minus AT. Here A is nothing but 1 by RC. So that E power minus t by RC. Right. So finally we got I of t equal to E by R E power minus t by RC. So based on this value. Now this we'll analyze the equation. E by R is the initial value of the current directed by I. So RC is called a time constant denoted by lambda. Right. So E by R is the current, initial current, and RC, this RC is the called a time constant of RC circuit. Right. So that the charging current I of t is equal to this E by R is replaced by I. E power minus t divided by lambda. Right. RC is the time, RC is the lambda. Here 1 divided by RC is available. So minus t by lambda. So this is the final equation for the current. I of t equal to I E power minus t by lambda. Right. We will see the further analysis. this charging current seems to be exponentially decreasing from equation 6, right? So e power minus this term normally represents decreasing. When the time increases, the current is decreasing. The charging current is decreasing. The initial current equal to value of I when t equal to 0 is I. The steady state current value of I when t equal to infinite, that is equal to 0. Initially current and keep on decreasing and it become 0. I will see the further analysis. So the variation of the current with respect to time is shown below, graphically shown below. This is the time. When the time increases, the current is keep on decreases. That is the observation we got from the equation, right? Initially it is I, then keep on decreasing. Similarly, we can analyze the voltage across the resistor and capacitor, ER and EC, right? ER equal to R into I, V equal to IR, right? I into R, that is equal to R into I. I is already we calculated, I e power minus t by lambda. R into I can be written as E, so e power minus t by lambda. So this is also decreasing in nature, right? When the time increases, voltage across the resistor decreases, right? In order to find the voltage across capacitor, ER plus EC equal to total voltage. So that EC equal to E minus ER. This term is brought this side. So E minus this ER is nothing but E into e power minus t by lambda. You take E outside. So that 1 minus e power minus t by lambda. This e power t minus t is a decreasing term, but 1 minus, so it become increasing. So the voltage across the capacitor is increasing. From the equation we can easily understand, right? This term is decreasing, but 1 minus is there, so that it is increasing, right? Now we'll see the graphical representation of this ER and EC. ER exponentially decreases from E to 0 as time increases from 0 to infinite. When the time increases from 0 to infinite, the voltage across the resistor is decreasing from E to 0. In case of the EC, the voltage across the capacitor, when the time increases from 0 to infinite, it increases from 0 to E. Both are different. E to 0 here, 0 to E. So that is given here. This is the time is available. The voltage across the resistor decreases from E to 0. Voltage across the capacitor increases from 0 to E, right? Graphically, the variation of ER and EC can be plotted as shown in the diagram. Now we'll see the time constant for the RC circuit. So the time constant lambda for the RC circuit, in equation 8, substitute lambda equal to t. The equation 8 is nothing but I equal to I e power minus t by lambda. Now we need to substitute lambda equal to t. So t got cancelled, e power minus 1. Otherwise 1 by e. So this value is 0.368 I. So what is this value? Thus the time constant for RC circuit is the time during which the current falls to 36.8%, because here the current is decreasing, right? So the time constant is time taken to fall the current to 36.8% of initial current. That is called a time constant. The current should decreases about this value, 36.8%. So in this video we discussed the TC transient response of RC circuit, resistor capacitor, charging, case 1 charging, discharging available in separate video. We analyze the current I of t, that is decreasing in nature. Then we analyze ER and EC also. ER is decreasing but EC is increasing. Finally we calculated the time constant also. Subscribe the channel for more videos and notifications. Soft copy of this material available in the drive. The link is given in the description box. Thank you for listening. Welcome viewers. In this video we will see the DC transient response of RC circuit, resistance and capacitance. Case 2 discharging. Subscribe the channel for more videos and notifications. Soft copy of this material available in the drive. The link is given in the description box. Now we'll go to the topic DC transient response of resistance and capacitance connected in series. Case 2 discharging. Charging, case 1 available in separate video. Now this resistor and capacitor is connected in series, that is energized by the DC source E. There are two positions available. The switch is S is there, position 1 and position 2. If it is connected in position 1, DC voltage is applied. If it is connected to position 2, DC source is disconnected. Right. Now we'll see what will happen during this position 1 and position 2. The switch has been in position 1 for sufficient time to establish steady state condition. So initially the switch is kept in the position 1 so that the capacitor start charging. It will give the sufficient time to get the steady state condition. Let this switch is moved to position 2 at the instant t equal to 0. Right? After some time, long time, it is position 2 is changed to position 2. Under steady state condition, the capacitor is fully charged. That is during the switching position 1. The voltage across C is E, which polarity is as shown in the diagram. Polarity is plus minus. This is the polarity, plus minus. Right? So initially at position 1, it is sufficiently charging and increasing the charging, increasing the voltage E with this polarity. Afterwards, it is moved to the position 2 at t equal to 0. Right. Now we'll apply the Kirchhoff's voltage law, KVL. What is the KVL? When it is at position 2, there is no applied voltage. So, okay, right. So it is equal to resistive drop and capacitive drop. That is applied voltage equal to resistive drop plus capacitive drop normally. But now during position 2, the voltage is 0. Right. So the resistive drop plus capacitive drop equal to 0. That is the KVL. While applying KVL or differential equation of this given circuit. The differential equation of this circuit is I into R, resistive drop, plus 1 by C minus infinite to T I dt, that is equal to 0. Here no voltage is available. So I into R plus 1 by C. This minus infinite to is split into two time periods. Minus infinite to 0. 0 to t. Minus infinite to 0 means initial condition. 0 to t means after closing the switch. Right. Now we'll take the Laplace transform on both the side. So this 1 by c integral minus 0 to t I dt is nothing but E. We already discussed that the switch is at position 1 for long time. So capacitor is charging and attain the polarity E. Right. So this term is nothing but E. So while taking Laplace transform on both the side, as I become I of s. We are converting t domain into s domain and R plus this term is nothing but E. So that E by s is clearly given here. This E. Laplace transform of E equal to E by s. Then 1 by c integral 0 to t I dt is nothing but I of s by s. Integral mean I of s by s. Differential mean s into I of s. That is equal to 0. Now we'll go for the further simplification. We can simplify this equation. So I of s into R plus 1 by c I of s by s. This E by s is brought to that side. So it becomes minus E by s. Right. This I of s is available commonly. Take outside. So R plus 1 divided by cs equal to minus E by s. Now brought this term in the denominator. So that I of s equal to minus E divided by s, minus E divided by s, and this term R plus 1 by cs. Now we'll go for the further simplification. So the multiply the s term inside so that it is R into s. Here 1 by cs is there, s got cancelled. So R by s plus 1 by c. Right. Now take the R outside. So that s plus, here only 1 by c is there, R is not there, so 1 divided by RC. So we got s plus a, this term, standard format, s plus a, so that we are taking R outside. Right. Now I of s equal to minus E by R into s plus 1 by RC. Now we can easily take the inverse Laplace, then only we will get the equation in time response, time domain. Take inverse Laplace on both the sides. So that I of s is I of t. Minus E by R is constant. 1 divided by s plus 1 divided by RC is nothing but e power minus t by RC. So based on this formula. 1 divided by s plus a equal to e power minus at. Here a is nothing but 1 by rc. So that e power minus t by rc. This a is nothing but 1 by rc. Right. In this 1 by rc is the lambda, time constant of the RC circuit, 1 by lambda. So here 1 divided by RC is lambda, right? So that is minus T divided by lambda, right? This is RC equal to lambda, not 1 by RC. So this is not 1 by the this RC equal to lambda. So that minus T divided by 1 by RC is available here. So that 1 by lambda, right? Minus T by lambda. This 1 divided by RC. RC equal to lambda, not 1 by RC equal to lambda. This RC is lambda, right? So that finally we got I of t equal to minus I. E by R is I, e power minus t by lambda. So this is the final equation. This from the analyzing the equation, e power minus t means it is a decreasing in nature, but in the negative region. Minus is there, so that it is a negative region, right? So the current is called a discharging current. So it is decreasing in a negative region from minus E by R to is actually increasing, but is due to the negative region, right? So minus, this is minus E by R. So this is called a discharging current. So in this video we discuss the DC transient response of the RC circuit in the discharging condition. The charging is available in the separate video, right? So subscribe the channel for more videos and notification. Soft copy of this material available in the drive. The link is given in the description box. Thank you for listening. Welcome viewers. In this video we'll see the DC transient response of RLC circuit with step input voltage. Subscribe the channel for more videos and notification. Soft copy of this material available in the drive. The link is given in the description box. Now we'll go to the topic. RLC circuit. Resistant, inductant, capacitor are connected in series. We are going to see the DC transient response with the step input. Let us consider the circuit. Resistant, inductance, capacitance are connected in series, energized by the DC voltage source E. This is the switch S. We can control the supply voltage by closing and opening the switch. This is the current flowing, current direction. In order to analyze that transient response, we need to go with the Kirchhoff's voltage law. We need to find the differential equation. By taking Laplace and inverse Laplace, we can obtain the transient response, time response. Now, applying KVL to the circuit, we are going to apply the Kirchhoff's voltage law to this circuit, so that the Kirchhoff voltage law is nothing but the supply voltage E equal to voltage drop across resistor, inductor and capacitor. So this is the KVL given. So the applied voltage E is equal to resistive drop, inductive drop and capacitive drop. Resistive drop is R into I plus inductive drop is L di by dt. Capacitive drop is 1 by C integral minus infinite to T I dt. That is equal to supply voltage E. So this is nothing but potential rise. This is potential drop. So this is the basic equation of of RLC circuit by applying the KVL, Kirchhoff's voltage law. Let us consider this equation number 1, right? Now we'll split the limit of this minus infinite to t. We are going to split into minus infinite to 0 and 0 to t. So this is the initial condition before switching. 0 to t means after switching, right? So that this is the normal minus infinite to t. While splitting into minus infinite to 0, this is called initial condition or before switching the circuit. 0 to t is immediately after closing the circuit, after closing the switch, right? This 1 by t, 1 by c integral minus infinite to t I dt is called a initial charge across the capacitor. That is assumed to be 0. Initial capacitor, there is no initial charge. So 1 by c integral minus infinite to t I dt is 0, right? So this term become 0. So only we have Ri plus L di by dt 1 by c integral 0 to t I dt, that is equal to E, right? This term become 0. So take this equation number 3. This is equation number 2, right? Now we need to take the Laplace transform. In order to convert the ST domain into S domain, we are going to take the Laplace transform. We are going to take the taking Laplace transform on both the side we get. So R into I means R into I of S. This I is the t domain. I of t is changed into I of S. Similarly L. This di by dt is nothing but S into I of S. Into Laplace transform of di by dt is S into I of S minus I of 0 plus. This is initial condition, plus this value 1 by c is there. So integral 0 to t I dt is nothing but I of S divided by S. Differential means S into I of S. Integral means I of S divided by S. Then Laplace transform of E is E by S. Right? Now we taken the Laplace transform on both the sides. This is the initial condition. Right? Now assume that I0 plus initial current is 0. There is no initial current. Already assume that initial charge also 0. So this term is 0. So R into I of S, L of S into I of S plus I of S divided by CS. This term is 0. That is equal to E by S. Now we can take the I of S common. I of S available in all the terms. So that R plus LS plus 1 by CS equal to E by S. Right. Now we'll bring this term in the denominator so that we are able to find the expression for I of S. So I of S equal to E divided by S already there. Bring the term in the denominator. R plus LS plus 1 by CS. Right. So now we got the expression for the IS, current IS. Now we'll go for the further simplification. Multiply the S inside so that it become RS plus LS square plus 1 by CS already there. So SS got cancelled, 1 by C. Right. So the S term available outside is multiplied. Now bring the L outside, because what we need is S square. We need a standard form S square. X square plus AB plus BC, like that we need S square. So that L is taken outside. Right. Here L is not available. So R into S divided by L. The L available is taken outside. So here also L is not available. So 1 divided by LC. Right. So this is the equation number 4. So it is in the standard form. E by L S square plus R by L S plus 1 by LC. So that is nothing but X square plus AX plus BC, like that. Right. Now R by L S plus S square plus 1 by LC equal to 0. We'll take this X equal to 0. Now we need to take the inverse Laplace transform. Before that we need to simplify this expression. Then only we can take the inverse Laplace transform. So that we are equating this term equal to 0. Now we can rewrite that S square plus R by L S plus 1 by LC equal to 0. So this is very similar to the quadratic equation. Ax square plus bx plus c equal to 0. Right. Here A is 1. X square, x we are treated as S square. B is nothing but R by L. C is 1 by LC. Right. So A equal to 1. We'll see that A equal to 1. B equal to R by L. C equal to 1 by LC. Right. Now how to find the square root for this quadratic equation? General formula is there. X equal to minus b plus or minus square root of b square minus 4ac divided by 2a. So by using the same formula we can able to find the root of this quadratic equation. Right. Now we'll substitute this. The all a, b, c values are available. By using that we can substitute. By using the same formula, you can write S equal to minus B. B is R by L plus or minus B square R by L square minus 4 into AC. A is 1, B is 1 by LC divided by 2A. A is 1. Right. Now all the values are substituted by the same quadratic general formula. Now substituted. Right. Now we can see that. So we can divide this S. We divide this 2 with the term. We split the terms. So R divided by 2L plus or minus square root of R divided by 2L square. This 2 is going inside the square root minus 1 by LC. So here 4 is available. When the 2 going inside it become 4. 2 square 4. 4 got cancelled. right? Only here we have 2 square, right? So the 2 is splitted, minus r by 2l. Here r by 2l the whole square. Here 4 and 2 got cancelled, right? Now we got this expression, minus r divided by 2l plus or minus square root of r divided by 2l the whole square minus 1 by lc. Now we need to find the roots for this expression. So let us consider minus r by 2l equal to alpha. The square root of r by 2l the whole square minus 1 by lc is beta, right? We'll take alpha and beta, so that we can write s equal to alpha plus or minus beta, right? So that is nothing but alpha plus beta into alpha minus beta, so that s equal to alpha plus beta, alpha minus beta, right? So that this term, this s square plus r by l, s plus 1 by rc is nothing but s minus alpha plus beta into s minus alpha minus beta, right? So s equal to alpha plus beta, so that we bring the term this side, means s minus alpha plus beta. Similarly s minus alpha minus beta. Now we need to verify for the different conditions, so that we can write the equation for us. I of s equal to E divided by L, already available. So here we can replace the equation, s minus alpha plus beta into s minus alpha minus beta, right? So that E by L, s into alpha, same thing, alpha plus beta, s minus alpha minus beta. Take this equation number 5, right? Now with the use of alpha and beta, we can go for 3 different cases. The roots are equal and same, the roots are real and same, the roots are real and different, and roots are complex conjugate. 3 different possibilities are available. This is general one. Now we'll see the 3 different possibilities one by one. So the case 1 is r by 2l the whole square is greater than the l by 1 by lc, so that we'll get the positive value. This is square root of r divided by 2l square minus lc. So this term is lesser, means we'll get the positive value. So the roots are real and different, not a complex conjugate. They are real roots, but they are different roots. Then how will you find I of s can be k1 divided by s minus alpha plus beta plus k2 divided by s minus alpha minus beta, right? We can write like this for your roots are real and different, right? So by simplifying, by taking inverse Laplace, we will get I of t equal to k1 e power alpha plus beta, the beta into t, right? So this is the inverse Laplace formula, plus k2 into e power alpha minus beta into t, right? So this is the formula, s minus a, s plus a, this is a formula, s minus a means e power at. By using that we can write this, right? Now this k1 and e power alpha t available commonly, so that is taken outside. So that we have k1 into e power beta t plus k2 into e power minus beta t. Here minus beta t is available, alpha t is commonly available, both alpha t is commonly available. So this is equation number 6. By analyzing the equation number 6, we can go for a conclusion. The current is said to be overdamped. For this equation, the current is overdamped. That is, when the time increases, current keep on increases, right? This is the rated current. The current is keep on increases. By analyzing that, we are able to understand. So the case 1, roots are real and different. We got the response of the time as overdamped, right? Now we'll go to the second case. Second case is both are equal. R divided by 2L the whole square equal to 1 divided by LC. So both got cancelled. There is no term. B square plus or minus term is there. So only one root. The roots are real and equal because the square root term is totally cancelled. So the roots are real and equal. So we can write I of s equal to k1 divided by s minus alpha the whole square plus k2 divided by s minus alpha. These are all the 2 different roots with the same value, right? So that by taking the inverse Laplace, we can write I of t equal to k1 into e power alpha t into t plus k2 into e power alpha t, right? Because of square we are getting t here, right? Here only s minus alpha is there, so that e power alpha t. Here s minus alpha the whole square, so that e power alpha t into t. Cube means t square. Power 4 means t cube. Like that it will increase. So e power alpha t commonly available. So k1 into t plus k2, right? K1 into t plus k2. By analyzing the equation we can go for a conclusion. So the current is to be critically damped. Critically damped means go nearby the rated value. Nearby rated value, right? Keep on increases, goes nearby the rated value, right? So the second case, roots are real and equal. The nature of the current is critically damped like this, decreasing gradually and reaches the critical value. Now we'll go for the third case. So the third case is this term is lesser. R divided by whole square less than 1 by LC. So what happened? Lesser mean we'll get the negative. So the roots become complex conjugate. The negative is replaced by I square. So we'll get complex conjugate, that is alpha plus j beta into alpha minus j beta. These are all the two different roots. Complex conjugate. One is plus, another one is minus. So that I of s can be written as k1 divided by s minus alpha plus jb plus k2 divided by s minus alpha minus jb. Here s minus alpha plus jb, here s minus alpha minus jb. So while taking the inverse Laplace, we got I of t equal to k1 into e power alpha plus j beta t plus k2 into e power alpha minus j beta into t, right? Only here alpha plus j beta, here alpha minus j beta, right? Now this e power alpha t is commonly available. The beta is here j beta, here minus j beta. So e power alpha t is taken outside. So k1 e power j beta t plus k2 e power minus j beta t, right? So this can be written as, the above expression can be written as I of t equal to e power alpha t a plus cos beta t plus b sin beta t. This is directly written. We can go for a further simplification is there, but not shown here. Directly written in a complex conjugate form. A plus cos beta t plus b into sin beta t. By analyzing this equation, we can go for a conclusion. The solution shows that current is oscillatory and at some time decays in a short time. The current is oscillating. So this is keep on oscillating. At one time it is decaying. Decaying means reaches the zero, minimum value. So oscillation at some time decays to short time, right? So the third case, complex conjugate, the nature of current is oscillatory and become a decaying at a short time. So in this video we discussed the RLC series circuit, transient response, right? After applying the KVL equation, we got the equation. While simplifying, we got three cases. Roots are real and different. In that case it is overdamped. Roots are real and equal. In that case, roots there, the current is critically damped. Third case, complex conjugate. In that case, the current is oscillatory and decays at a short time. Subscribe the channel for more videos and notification. Soft copy of this material available in the drive. The link is given in the description box. Thank you for listening.